This begins EE 555 on Thursday, April 10, 2014.
Thank you very much. What happened? No. Wrong direction. Wrong. The chart is wrong direction, my dear. No. Yeah.
Sorry.
Yeah, that's fine. Thank you very much. Good morning, everybody. Let's continue our discussion from last time. We started looking at optical network technologies. Optical technologies are the heart of the broadband networks. The heart of the broadband networks is in the optical technologies. And we are going, as we said last time, we are going to be looking at two types of these technologies. The first one, which is referred to as the SONET. A SONET is the synchronous optical network, and the other one is the DWDM. DWDM stands for the dense wavelength division multiplexing. Dense wavelength division multiplexing. And again, as I told you last time, DWDM is purely a physical layer specifications or characteristic, if you would like, or layer, whereas the SONET can go a little bit higher than the physical layer. SONET might run over DWDM, not the other way around. Not the other way around, as we will see in shortly. So let's start with SONET. Again, it stands for the synchronous optical network. A little bit of a misleading because SONET actually defines an interface, an optical interface. And it also defines a synchronous multiplexing scheme for trap or format, synchronous multiplexing format for carrying all of these types of all of these types of services that used to be served by the digital hierarchy. Why they establish it? By the way, it is established, or it is based, everything is based on a 51.84 megabits per second. They refer to it as an OC1. I will show you where this number came from in just a second. 51.84 megabits per second. Before we get into this, let me show you. This is the digital hierarchy in the US. In the US, digital hierarchy. In the digital hierarchy, they started, everything was based on the DS0. DS0 stands for digital signal level 0, which supports only one voice circuit at a rate of 64 kilobits per second. Bandwidth or a rate at 64 kilobits per second. Then they multiplexed 24 of these. They multiplexed 24 of these to generate what is known as a DS1. A DS1 is what is referred to as the service, is referred to as what? T1. When you hear DS1, DS1 is the level of the signal. T1 is the name of the service. T1 is a service. So DS1, T1, which consists of what? 24 channels, 24 voice channels at a rate of 1.544 megabits per second. Then they came up to a DS2. DS2 supports 96. When I say 96 voice circuits, it means what? DS2 is equal to 4 DS1. So if you multiply 4 by 24, you get what? You get 96. Again, as I told you last time, this one did not prove to be very successful. This service did not prove very successful. This one did, which is what? Which is the DS3. DS3 supports 672 voice circuits. 672 voice circuit, which is what? Which is multiplexing of 28 DS1s. So you take 28 of DS1s, you multiplex them, you get what? You get DS3 at a rate of what? At a rate of roughly 45 megabits per second. And they stopped here. That's where it stopped. That's the digital hierarchy. This, when I say digital hierarchy, means what? Pre-optical fiber. Pre-optical. The pre-optical, before optical fiber came into existence. That's where it stopped. 44.736 megabits per second. This one was, by the way, provided either over cable or a microwave link, not over a twisted pair. Twisted pair cannot support that rate. So it's over microwave links or over what? Over cable, over satellites, they can support what? They can support T3. But it stops in here. They found that there is a need to what? To come up with a new standard, a new hierarchy. The new hierarchy came after the advancement in the optical technology, and they came up with the hierarchy, which is referred to as a what? Which is referred to as the SONET. And the SONET was based on the OC1. Now, when they choose OC1, I'll show you how they chose OC1. When they chose OC1, they made sure that the rate of OC1 is higher than what? Is higher than all of these rates. To allow for what? To allow support for all of these rates as what? In the SONET frame. Clear? In the SONET frame. In other words, the SONET frame can support any one of these. Excuse me. Any one of these rates can it be supported? It can be supported by OC1. Then what did they see? They see that the OC1, the 51.84 megabits per second, is nothing. So they build what? They build a hierarchy on top of what? On top of the OC1 by multiplexing several of those OC1 into bigger levels. So they came up with what is known as what? OCN, level N. And OC level N, the beauty of SONET is that OC level N is exactly the same as N times what? OC level what? Level 1. So, for example, if we talk about OC3, this is what? 3 times what? 51.84, which is what? Which is 155.52 megabits per second. Unlike the what? Unlike the digital hierarchy. In the digital hierarchy, for example, when we said DS2 is equal to 4 DS1, when we say DS2 equal to 4 DS1, if you take this one and you multiply it by 4, you are not going to get exactly this number. You are not going to get exactly this number. Clear? If you multiply this, in other words, 1.544 times 4 is what? 6, 7, help me. 6.176 megabits per second. Is this the same as this? No, it's not the same. Why? Because in the digital hierarchy, as you build the hierarchy, you needed to add what? You need to add more framing bits to establish what? Synchronicity. In SONET, as I will show you in just a second, it's the same what? It's the same type of what? It's the same type of a frame that you are going to be using. Clear? It's the same type of frame that you are going to be using. Increasing the rate just represent what? Multiplication by a number, just a number. Clear? Currently, by the way, OC192, which is equal to what? Which is equal to 192 times what? 51.84. This is roughly what? Roughly 10 gigabits per second. And again, as I told you last time, work is being done also on going into OC768. OC768, which is roughly what? 40 gigabits per second. All of these, by the way, the higher rates, as we'll see shortly, they will what? They will be supported by multiple wavelengths. And those wavelengths happen to be what? Very densely located near each other. That's what the D stands for. D stands for what? Dense wavelength division multiplexing, supporting multiple fibers, supporting multiple wavelengths on a single what? On a single fiber, which we'll see that in just a second. Okay, so again, the SONET was established to provide for an open optical standard. At that time, companies which were developing optical equipments, they were all what? Proprietary. They were all proprietary. They did not adhere to a certain standard. They were not able to talk with each other. So every company have their own product, another company have their own product, but they cannot what? They cannot talk with each other. They needed to establish an optical standard, and that is what is referred to as the SONET. Okay. Now, again, this is another chart that shows you digital hierarchy. By the way, you notice the DS4 here, they went a little bit what? Higher than DS3 by 6 times. In other words, DS4 is what? 6 times DS3. But this is not a standard. It's not part of the standard. So the standard actually stopped in here. The European standard, which is also adopted in other parts of the world, like in India or in China, they use the European standard. The European standard started again with E1. Again, everything was based on the 64 kilobits per second. You do remember how the 64 kilobits per second came from? Sampling the voice at a rate of what? 8,000, and then what? Quantizing the voice into 256 levels and encoding every level by 8 bits. So you got what? 8,000 times 8, which is what? 64 kilobits per second. Okay. However, the European standard went all the way up to what? Up to E5. Now, in the E5, at that time, they wanted what? See, in the case of the US, they started with what? With an OC1. With an OC1, because it was what? Higher than this rate, higher than the DS3, but the European, they needed something which is higher than what? The E4. E5 was not a standard. This one is not a standard. So they needed something which is higher than this one. So the European started from what? Started from the OC3 rather than the what? OC1. You follow me or not? To support all of these existing services. Clear? We will see that in just a second. So they came and, they named their hierarchy. They call it SDH. SDH stands for what? Synchronous digital hierarchy. Synchronous digital hierarchy, whereas SONET again stands for the synchronous optical network. They call there again, as I told you, everything was based on what? Was based on OC3. On OC3, which is the one? Which is the 155.52 megabits per second. Now, I want you to understand what this means, the payload rate. I will show you that in just a second. The total rate is 155.52 megabits per second, but the actual payload rate is what? 148.608 megabits per second. What does that mean? It means the rest is used as a what? As a header, to support a header, to support the functionality. Clear? Same thing with this one, OC12, which is what? STM. STM stands for the synchronous transport multiplex. Synchronous transport multiplex. Clear? Clear? Okay. This is the OC192 that I was telling you about a moment ago, which is roughly 9.95 gigabits per second, and it's equivalent to an STM64. STM64. Clear? Okay, good. Now, so what is the advantage to the corporate users? By the way, you notice why am I emphasizing corporate user? This is for corporation. This is not for what? This is for businesses, not for residential customers. Or residential customers are not going to have SONET extended to their homes. Clear? So what do they get advantage? The first advantage, of course, is that they provide a standard optical interface. A standard optical interface allowing corporation to buy their product from different from different sources. Does not stop at the S3 rate of this. It supports 51.84 gigabits, 51.84 megabits per second, all the way to what? Let's change this, please, into what? Into 10 gigabits per second. 10 gigabits per second. It provides for synchronous mode of operation. And this is the point that I need to emphasize. If you remember from last time, we took this example, just simple example. Let's assume this is LA here, and this is Chicago, and this one is in New York. And we do have what? We do have a T1, this is a T1, and this one is also a T1, connecting 3 branches of the same company. Let's assume this is a company. We have 3 branches in LA, in Chicago, and in New York. The T1 consists of what? Consists of how many channels? 24 channels. Now, let's assume 12 of them, does not have to be 12, it's just an example. Let's assume 12 of them are destined to where? Chicago, and the other 12 are destined to what? New York. Now, in Chicago, there are what? 12 channels. 12 channels means what? 12 voice calls. Think about it. 12 channels that are destined to what? New York. So what in the digital hierarchy, this is what is done. You receive the T1. You demultiplex the T1. Demultiplex the T1 means what? Recover all the what? All the 24 channels. Drop 12 of them, add what? 12, and what? Multiplex again. Did you understand or not? In other words, you needed a back-to-back multiplexer, one to D, in other words, like this, this, you drop what? You drop 12 of them, and you add what? Another 12 of them. Are you following or not? And then what? Multiplex them again. Did you get this or not? In SONET, as we will see, you don't need to what? To demultiplex them. You could drop them from the frame without demultiplexing the frame. You drop them from the frame without what? Demultiplexing it from the frame. Demultiplexing the other channels from the frame. So you drop these channels. Are you following me? You drop these channels and you replace them by what? By other channels, but without what? Demultiplexing all the way to the what? To the lower rates. All the way, for example, in this case, to the rate of what? 64 kilobits per second. The SONET, again, provides or it allows for add and the drop of time slots without bringing all the signals down to the what? DS1. So it eliminates the back-to-back multiplexing. It's more efficient switching, transport, cost savings, and so on. So it also improved the connectivity as a backbone technology. Most of the backbone right now, most of the backbone technologies are based on what? Are based on SONET. Clear? Improved connectivity as a backbone technology, and it also improved the diagnostic and the fault tolerant. Fault tolerant means what? Means if there is a failure in the network, you don't want the entire thing to what? Bogs down. You want it to be able to what? To still operate, maybe at a lower rate. Still operate until what? Until technicians comes and try to figure out what the problem is and fix it. That's what it means by fault tolerant. Fault tolerant means what? When you design something and you say this design is a fault tolerant design, it means that if faults do occur, you do have what? You do have temporary solution to them before what? Before you say what the network is what? Is all the way down. And I will show you that in just a second. Now, let's look at the what? Let's look at the protocol stack, the transmission protocol stack. Now, what do you notice in here? You notice in here that there are 4 layers, but in reality, if you compare this to the what? To the OSI model or to the TCP/IP model, this one, all of it is equivalent to what? Equivalent to the functionalities of what? Of a couple of layers. Clear? A couple of layers. So try to understand the terminology and the equipment that is used. Okay. Now, first of all, in the different types of equipment, we have SONET equipment. The first one is what is known as a path terminating equipment. Path terminating equipment, PTE. And this one here, this type of equipment will have all the what? All the layers implemented in them. All the layers implemented in them. The second device, we refer to it as a what? Section terminating equipment. Section terminating equipment. This one terminates sections. What is a section? A section is a what? Is the portion of the link between what? One device and the next device. One device and the next device. So this is one device. This is another device. They are connected by optical fiber. This is called a what? A section. This is one section. This is another section. This is a third section, and so on and so forth. Devices that terminate sections are called what? STE, which is section terminating equipment. In the section terminating equipment, you only have what? A couple of layers. A couple of layers. I want you to think about the section terminating equipment the same way as you thought about what? Switches. Layer 2 switches. Think about it as layer 2 switches. Then we do have what is known as a what? A line terminating equipment. A line terminating equipment. This one, excuse me, this one will terminate lines. Will terminate lines, which means what? It does not go all the way to the what? To the path layer. The line terminating equipment is the devices that we just referred to them as what? As add, drop, mux. Add, drop, mux. They are multiplexers. They add channels and they drop channels as per needed basis. We call it what? A line terminating equipment. And then the other side, of course, is the path terminating equipment. The layers are what? The photonic layer. Photonic layer is the same as what? As a physical layer, because you are using what? Photonics. These are the optical signals. Photonic layer, the section layer, the line layer, and the path layer. Now, what comes on top? What comes on top is the services that is carried by SONA. What is? Is DS1, DS3, ATM cells, and so on and so forth. All of these existing services are going to what? Are going to be supported by SONET. SONET is the what? Is the support for all of these services. All of these services, as I will show in just a second, will get encapsulated inside SONET frames. In other words, the SONET frame is carrying what? DS1 signals, is carrying DS3 signals, is carrying ATM cells, and so on. So all of these things. Clear? Okay, good. Now, briefly, let's look at the description of each one of these stacks. The photonic layer, which is the, again, as I told you, the physical layer. What does this one do? It provides for specifications of the optical fiber, how much required power, what is the dispersion characteristics of the transmitting laser, what is the receiver sensitivity. Receiver sensitivity means what? What is the minimum power that the receiver can or need to detect the signal, and so on and so on. So you can see from the functionality that it deals with what? It deals with physical layer. It deals with physical layer things. Section layer creates the basic SONET frame. Now you can tell which layer it is. When we talk about what? SONET frame, we are talking about what? Which layer? Layer 2. So this one will create the basic SONET frame. The basic SONET frame is the what, by the way? Is the what? Is the OC1. Is the OC1, the basic SONET frame, which I will show in just a second. It will also do the what? Scrambling, it do error monitoring. Scrambling means what? Means it interleave bits from what? Multiple channels, such that when errors occur, if you are going to scramble your what? You are going to scramble your data, not all the channels will be what? Will be affected. Some of them will not be affected, some of them will be affected, and so on and so on. The line layer is responsible for establishing synchronization for multiplexing of the data onto the what? SONET frames. In other words, multiplexing all of these what? All of these services onto the what? Onto the SONET frame, along with switching, protection, maintenance functionalities. The time is 18 o'clock. The path layer responsible for end-to-end transport of data at the appropriate signaling rate. It maps services into the what? The SONET payload frame or format. It maps all of these what? All of these. For example, In ATM cells, every one of them is what? 53 byte long. What does it do? What does the path layer do? It takes what? It takes all of these 53 byte ATM cells and maps it into what? Into a format that can be supported by what? By the SONET frame, which I'll show you in just a second. Clear so far? Okay, good. Now, let's look at the frame. How does the frame look like? And we see the strange thing. Let's look at the strange thing about it. What is the duration? What is the frame duration? The frame duration is 125 microseconds. Is that the same duration? Is that the same duration as the T1? That's the same duration as the T1. Clear? Clear? Okay. It's the same duration of the T1. But what do they put here? They put more bits. More bits. Do you remember how many bits in a T1? In a T1 frame. Do you remember how many bits? Number of bits? You forgot? There are 24 channels. Each channel is what? 8 bits plus what? 1 framing bit for a total of what? 193 bits every what? Every 125 microsecond. Every 125 microsecond. Clear? Okay. Now, clear? Let's see in the OC1 frame. How many? The duration is still what? The duration is still 125 microsecond. It's the same duration, but they put more what? They put more bits. How many more bits? Let's see. The frame consists of what? Consists of 9 rows, and 90 what? Columns. 9 rows and 90 columns. Now, I need you to understand one thing here. Even though I'm sketching it vertically, but remember, when you are transmitting these bits, the transmission is what? This way. Here, and then what? Here, one after the other in a serial fashion. Clear? Clear? Okay, good. Now, so what does that mean, by the way? When I say serial fashion, what does it mean? It means at the beginning there are what? Some header bits, followed by what? Payload bits, followed by a header bit, followed by what? Payload bits, followed by what? A header bit. Did you get my point or not? You are not transmitting the what? The header contiguously. You are transmitting what? Header bits, payload bits, header bits, payload bits, and so on and so forth. Clear? Okay. So what do we have? We have 9 rows, and how many columns? We have 90 columns, for a total of what? 9 times 90 times 8. Where is the 8 came from? It's 8 bytes. This is what? 9 rows. Every one of these is a what? Is a byte. So when I say 9 rows means what? 9 bytes. Are you following me or not? And 90 what? 90 columns. Everything is in byte. So it's what? 9 times 90 times 8 divided by what? 125. Divide by 125, which is what? 125 microseconds from here to here. You get what? You get the 51.84 megabits per second. Did you get where did this came from? The 51.84 megabits per second? Clear? Okay. Now, out of this, how much is payload? Out of this RAID, how much is the payload? The header occupies what? The first 3 columns, and what? 9 rows. And then there is also one header, which is what? 1 column. I will show you what this means in just a second. That is in the payload. Clear? That's in the payload. For a total of what? So what is the real payload rate? The real payload rate is what? 9 times what? 86. Did you answer where the 86 came from? 9 times 86 times 8 divided by what? 125, which is what? Excuse me, which is the 49.54 megabits per second. Clear? Clear? So the total is what? 51.84 megabits per second, but you are only going to get out of it how much? 49.54 megabits per second. Enough, by the way, enough to support a what? A T3. A T3 is how much? 44.736 megabits per second. So this one is high. Okay, now let's look at the headers. We have 3 different headers. The first one is what? Section overhead. Section overhead. Where is this one going to be processed? Where is this one going to be processed? This one is going to be processed at what? Every time the section is what? Every time the section begins and every time the section what? Terminates. Clear? Section begins, section terminates. So it's what? 3 by 3, which means how many octets? 9 octets. Then you do have the what? The line overhead. The line overhead. Where is this one going to be established? Where is this one going to be inserted? It is going to be inserted in the line header, in the line layer, and it's going to be what? Processed in every device that has a what? Line layer in it. In other words, will this one see a line header? This one will not process a what? A line header. I want you to understand these headers the same way as you understood the following. Does the frame in TCP/IP, does the frame has a header? The frame has a header. Does the packet has a header? The packet has a header. Does the TCP has a header? TCP has a header. Where is the frame header being processed? The frame header being processed in every device that has layer what? Layer 2. The packet header is processed in every device that has a what? Layer 3. The TCP header is processed in every device that has a what? Layer 4. Same idea in here. So this is what is processed in every device that has a what? Has a section header, a section layer. This one is processed in every device that has a line layer, and this one is processed in the path overhead. Now, one more thing before I show you how they multiplex that. One more thing. You see this path header? They wanted what? They wanted the SONET to be what? To be synchronous. See, in a T1, listen to me, in a T1, which is synchronous, 24 channels, if you don't have data, excuse me, if you don't have data ready to be transported by a T1, you still need to generate the frame to establish synchronicity from the transmitter and the receiver. If your data come in the middle of a time slot, you have to wait until what? Until the next time slot. You follow me or not? They wanted the SONET not to be that way. They want the SONET is that whenever the data becomes what? Ready, I want to be able to what? To support it. I don't want to wait until what? Until next time to come and so on and so forth. So they did what? They put the header, the path overhead. Remember, the path layer is the one that will what? That will support the data. That will support the data, the services. They put the path header overhead in the payload. In the synchronous, this one they call it SPE. SPE stands for the synchronous payload envelope. They put it in the payload and they made it what? Variable position. Variable position. What does variable position mean? First of all, where is the real payload starts? The real payload will start with the first byte after the what? The path overhead. After the path overhead, which means what? Where is this one starting? This one is starting. Where is this real payload starting? Real payload is starting here. And this one is what? Is movable. So for example, if the data is ready, where is this one going to be? This one going to be in here. Are you following or not? And the data right away will what? Will be supported. Did you get this or not? In this example, what happened? During this time, there is no what? There is no data. You follow me or not? So they moved the what? They moved the header to this side to indicate that the payload actually starts where? Here. How does it go? Tell me, how do you continue with this? This is how you continue. You go this way, and then what? Are you following me or not? Okay, and if this one was here, the data will go what? Will go this way, this way, this way, this way. This one is what? Is movable. And the payload starts after the what? After the path overhead. The payload starts after the first byte of the path overhead. Now, in the header in here, which I'll show in just a second, there is a pointer pointing toward where? Where is the path overhead byte? The first byte of the path overhead starts. So from this, they can tell where is this one is heading. This one is movable. This header is movable. Clear? Clear? Okay, good. Now, this is the header. The header, which I'm not going even to go through it. This is all having to do with what? To do with error detection, with the protection stuff, with some pointer. I just want to show you this. Do you see those pointers? Pointer 1, pointer 2, pointer 3. In which header? In which header? Sorry, in which overhead? In the line overhead. Do you see the line overhead? These pointers will point toward the start of what? The start of the payload, the actual payload. In the section, by the way, all what you need to do, all what you have is what? It's framing stuff or error detection and so on and so forth. That has nothing to do with the what? That has nothing to do with the actual what? Actual services that is being multiplexed. Clear? Oh, good. Don't worry about all of these. I'm not going to ask you any one of these things. But I need to understand the basic concept that they what? They made this one movable so that the data can be supported immediately as they what? As they arrive. You don't need to wait until what? Until the next frame. Now, in doing so, is it possible that your data, is it possible that your payload or your data will straddle into 2 consecutive frames? 2 consecutive frames means what? Is it possible that the data arrives in here? Yeah, where would this one be? I'm not sure. Did you get my point? Let me show it to you so that you understand what I'm talking about. I will show you this. Tell me here what happened. I want you to see this. Where is the sonnet frame? The sonnet frame is this one. This is one sonnet frame. What is, in other words, where is the 125 microsecond? There's the 125 microsecond here. This is one frame, and this is another frame. Are you following or not? And when was the data ready? When did the data arrive? The data arrived in here. It did not arrive in here. Did you get my point or not? What happened here, by the way? What happened here? Nothing. Nothing. It was what? It was not occupied because there was no data. Are you following or not? Now, the data, when it came here, it does not have to wait until the what? The next frame. Because in Sonnet, the data does not have to start at this point. Did you get my point or not? It will start whenever it's what? Whenever it's ready. Whenever the data is ready, that's where the payload starts. So where did it come here? Show me where did it come here. The data in here. So the path payload in here. Now, the entire payload, did it fit in one frame or in 2 consecutive frames? In 2 consecutive frames. Are you following me or not? Yes or no? In 2 consecutive frames, we say what? We say that the data has been straddled into what? 2 consecutive frames. By the way, could it be on 3 consecutive frames? How? How could it be? How? Let's assume the data came in here. Let's assume the data came in here. Then it will what? A couple of bytes will be here, and the remaining is what? Is here. I'm not sure. Did you get the point? Did you get the point or not? It cannot be in its what? 3 consecutive frames. It can be at most in what? In 2 consecutive frames. It cannot be in 3. No, you didn't get it. How big is the payload? How big is the payload? The payload is this. 1 second. Where did I put? 1 second. I don't know where I put it. 1 second. Here. How big is the payload? How big is the payload? It's 9 times what? 86 times 8. Yes? let's assume that it came here. Let's assume that it came here. Will it fit in one frame? It will fit in one frame. Why? By the way, where would this path overhead be? If the data is ready here, where would the path overhead be? The path overhead will be where? Here. Did you get this or not? And will the data fit in one frame? It will fit in one frame. In here, did it come here or did it come here? It came here. How many frames does it need? It needs 2 frames. Could it need 3 frames? It cannot need 3 frames. Are you following that? The total is what? Is 9 times what? 86. Are you following that? It's 9 rows and what? 86 columns. Clear? Clear? Oh, so it starts in here. How does the equipment know that it's starting here? How does the equipment, the SONET equipment, the line, for example, line equipment, how do they know that it's starting here? In the header, in the line overhead, there is a pointer pointing toward what? The location in here. Think about this as a what? As a matrix. Are you following that? And this one is going to what? Pointing toward what? This row and this what? This column. That's the start of the what? Of the payload. And then you what? You move this way, this way, this way, this way, this way, this way, and so on. And we say that the SPE, the synchronous payload envelope, has straddled or can straddle 2 consecutive what? Frames. It can straddle 2 consecutive frames, not 3. It cannot go over 3 frames. Clear? Clear? Okay. So this is the example. This is a pointer in here pointing toward here. Then this is the data continuation. This one pointing here. This is the new data. This, look at the path overhead here. The path overhead in this frame is this. It is straddling here. Yes? The path overhead of the next frame is where? This. Did the position change? Look at the path overhead from one frame to another frame. Did the position change? The position did change. Did you get my point or not? Let's assume this one was in here. Where would the other one be? This one here. Let's assume this one was here. Where would the other one be? It will also be here. Did you get my point or not? But this one here, and by the way, what is the difference between this one and this one? How many bytes? Between this and this. How many bytes between them? It's 9 times what? Times 86. 9 times 86 between them. Clear? Oh, and there is, again, as I told you, there is a pointer here pointing toward where the start of the payload is. Oh, now, let's look at the multiplexing, synchronous multiplexing in SONET. Now, remember, an OC1 is called the optical carrier level 1. STS1, this is the signal. This is the signal. This is still part of SONET. This is not the SDH, the European one. SDH stands for, it uses what? The word STM. This one is STS, which is what? The synchronous transport signal level what? This is the digital signal. This is the what? Optical signal. Do they have the same rate? Both of them are what? 51.84 megabits per second. This is just the name of the what? Of the signal. The name of the signal. They call it what? STS1. The optical carrier is when it goes over what? Over the optical fiber. Let's see if you can help me before I show you this. How do we multiplex them? Look how we multiplex them. What is this? This is an OC1. What am I trying to generate? I'm trying to generate an OC what? OC3. What is OC3? OC3 stands for what? Optical carrier level what? Level 3. And what is the rate? What is the rate? Equal to what? 3 times what? 51.84. Which is what? 155.52 megabits per second. I want to show you why in SONET you just need to multiply by that number. In other words, you are not going to add more what? more headers in the what? In the frame, in the basic frame. Let's see. What do I have here? I have 3 OC1s. 3 OC1s or 3 STS1s. Each one at what rate? What is it? 51.84, 51.84, 51.84. How many rows in here? How many rows? 9 rows. Yes. How many columns? 90 columns. I wanted to see this. What is this? This is an STS3 frame. How many rows? 9 rows. How many columns? 200 and what? 70. Are you following or not? Yes? So what is the total? It's 9 times what? 270. Whereas this one, what was it? 9 times what? 90. Did you get my point or not? I did not add what? I did not add more things that were not available in here. Are you following me or not? So what do they do? Listen to me what they did. Okay, by the way, where is the 125 microsecond here? Here. Where is the 125 microsecond? The 125 microsecond is from here to where? Here. Yes? Here to here. Here to here. Every one of them is what? 125 microsecond. Can you show me where is the 125 microsecond here? The 125 microsecond is from where? Here to here. What does that tell you? Does the frame has the same duration? Does the frame have the same duration? It has the same duration, but it has how many more bits? 3 times as more bits. Did you get my point or not? Which means what? The rate increased. Did you get it or not? It's the same duration of the frame. The frame is still what? 125 microsecond. But instead of putting in here, how many bits am I putting in here? Total, including the overhead. It's 9 times what? 90. In here, how many bits am I putting? 9 times 90 times what? 3. I increase it by what? 3 times. Did you get this or not? Squeeze it. Squeeze it. What does it mean? It means the bit duration became what? Narrower by what factor? By a factor of 3. Because it's squeezed in the same duration. Clear? Okay. How do they do? Listen to this. They take what? 1 column here, put it here. In other words, it's, by the way, it's byte by byte. So follow me here. 1 byte from here, 1 byte from here, 1 byte from here. How many? How many here? How many here? How many columns do I have? 3. Here, how many columns? 3. Here, how many columns? 3. Guess how many columns here? 9. Did you understand where the 9 is? I say what? 1 from here, 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 1 from here. Did you get my point or not? How many in here? How many in here? 87, 87, 87. Yes? How many in here? 87 times what? Times 3. Are you following or not? Interleaving the bytes. When I say bit, I meant what? Byte. Byte, 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 and so on. So. Clear? Okay. But in doing so, they needed, first of all, to make sure that the STS, when they came, this is the MUX, this is the Sonnet MUX. When the STS1s comes, those are the STS1 frames comes. Before they get multiplex, they need to be, first of all, what? Aligned. Did you understand what I just said or not? They needed to be what? Aligned. When they come, are they coming aligned or not? They are not coming aligned when they come from different locations. Before they get multiplex, they get what? They get aligned together before they what? Before they multiplex it. Clear? How would you generate OC12? Can you tell me how do you generate OC12? OC12 is what? 12 of these. Yes? Which means what? This one will become what? How many? 36. Why? Where did the 36 come from? 3. And how many of them? 12. It's 36 in here. This one also will be multiplied by the same factor. Are you following me or not? And that's what I meant a moment ago when I said to generate an OCN, all what you need to do is what? Multiply N times what? OC1. Everything is OC1. You are not going to add a new framing bits. Whatever the headers in here will be in here as well. Clear? Okay. So you need to what again? The each STS signal is synchronized to the local STS1 clock at the multiplexer. So when it comes in here, this is a multiplexer, has its own clock, then this needs to be what? Synchronized with it. This one, you understand what byte interleaving means? Byte interleaving is what? It will take one byte from here, one byte from here, one byte from here. Then what does it do? It go and take what? One byte from here, one byte from here, one byte from here, and so on and so forth. Clear? Clear? Okay, good. So each STS signal is synchronized to the local STS1 clock of the multiplexer. The section and the line overheads, the section and the line overheads of the incoming STS1s are terminated, and its payload is mapped to a new STS1 frame that is synchronized with the local what? With the local clock. Clear? So as it comes, as it comes at what? As the signal comes to a multiplexer, where is the multiplexer? This is the multiplexer. These are going to be what? Terminated. Terminated means what? A process. And then what? It goes down. Are you following? It goes down. You are going to create a new what? A new frame. You are going to create a new frame. It's the same duration, but it's what? It's more bits in that frame. It's more bits in that frame. Always remember, a mux, you have what? You are writing into the what? You are writing into the mux, and you are writing at a certain clock, but the mux will read it at a what? Will read it at a much faster what? At a much faster clock. And in the same what? In the same duration, he reads what? He reads traffic from what? From all of them, rather than just from one of them. Clear? Because he's working faster. Pointers, again, in the line sections of the new STS1 frames may require some adjustment. They might require some adjustment. Why? Because you are going to what? You are going to multiplex all of these things. But mapping is done on the what? On the fly. Do you understand what on the fly means? As they come, they map it to what? They map it to the clock of the sonnet. Are they coming aligned? They are not coming aligned. As they come, they map it on the fly, such that they become what? They become synchronized before they get multiplexed. Clear? Okay, good. Now, this is the higher rates that I just explained it to you. But by the way, can they multiplex STS3 to generate STS9? STS3 to generate STS what? 9. What do? Same idea, but instead of working on this level, they work on what? That level. How many of these do I have? 3 of them. And again, they interleave to generate. Still at what? What is the duration of the frame? The duration of the frame is always what? 125 microseconds. The duration of the frame is always 125 microseconds. Okay. And finally, let's look at some topologies that are used for a sonnet. We have, first of all, the point-to-point topology. Let's look at the point-to-point topology. Again, we are talking about what? Business environment, corporations, and so on. We are not talking about residential. So here we do have a business. In the business, they do have what? They do have a PBX. What is a PBX? PBX is a private branch exchange. This is for the what? The local phone service. Are you following? Local phone service. So PBX, we do have what? Several T1 muxes here. We do have a LAN, local area networks, routers, bridges, and so on and so forth. All of these are what? Generating traffic. They get what? They get multiplexed with what? When a sonnet equipment, this sonnet equipment is located where? At the customer premises. At the customer premises in the company. And then it gets generated or in the photonic layer. In the photonic layer, the digital signal will be converted to optical signal that goes over a pair of fiber. This is the fiber here. Clear? Clear? Okay, to where? To the sonnet equipment in the central office. So we call it a what? A point-to-point. A point-to-point from the customer to the what? To the central office. Clear? Clear? Okay. Notice, by the way, in here, I just write OC1. It's just an example, but in reality, it's much higher than OC1. Are you following? Not if the corporation is big OC1 will not be high enough. 51.84 megabits per second is not much. Clear? Okay. Now, then we do have the other topology, which is called what? A point to multi-point. This is the one that I was just telling you about here. A point to multi-point. So what do we have in here? This is one point, this is another point, this is a third point, this is fourth point. Several what? Several digital signals in here are what? Are multiplex. Demultiplex, some of them are going to be what? Switched. DSX stands for what? Digital. The digital cross connect. Digital cross connect, they call it SX. Digital cross connect, level 1. Level 1 means what? They are dealing with what? Level 1 signals. You see the back-to-back? This is the back-to-back. That's the digital technology. Digital technology. Now look at the SONET. This is the digital technology. This is the SONET. In the SONET, what do we have? These are the signals that get multiplexed. In here, we have ADM. ADM stands for what? Add, drop, mux. Add, drop, mux. We don't have a what? The back-to-back. We don't have the back-to-back. We have an add, drop, mux. Some of them will be what? Dropped. Some of them will be what? Added. But you don't need to what? To demultiplex it. In other words, it's like you have the frame, you are picking what? Some of the channels, and you replace what? Other channels in place of them without what? Without demultiplexing all the channels. Without the demultiplexing all the channels. Which means the other channels remain in their what? In their time slot. You just what? On the fly. You just what? Remove the channels, put different channels in the place of them. We call them add, drop, mux. So again, this is the digital, this is comparison. This is the digital hierarchy. This is what? SONET. Clear? You just need to use a what? An add, a drop, mux. Here we have what? Several DS1s. Here we have several DS1. Some of them are, by the way, when it says dual OC1, it means what? It means like this. Clear? Dual means what? Dual. Clear? Okay. The third one, third topology, is what is referred to as what? A hub-based. A hub-based. We have what? Several SONETs in here. Several SONETs in here. SONET mux with several inputs. 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 And then what? We do have a centralized hub. A centralized hub. So, for example, in here, you could have what? Listen to this one. Signal comes in here. It can be dropped in here. Switch to here. This one goes to here. This dropped in here. Switch to here. It will go this way. Are you following or not? It's multiple locations. Multiple locations. The difference, this one is a what? Is a point to multi-point. This is one location, from one location, and I'm going to what? To multiple locations. And here is what? Hub-based. We have multiple locations, traffic going from what? All of them, between all of them. So we have what? We do have the digital cross-connect. We will study this when we get to the optical network architectures in just a second. Clear? Oh. But the most widely used architecture is what is known as a what? As a ring topology. The most widely used. This is the actual network. Let me show it to you so that you can see. This is what you see. This is the real world. This is the real world. This is the AT&T, the what? The Verizon, the Sprint. This is all of their networks. High-speed rings. SONET rings, SONET rings, SONET rings. Why did they adopt the rings? As I will show you in just a second. This is a ring. Now, first of all, what do you notice? You notice that there are what? There are two concentric rings. One on the outside and one on the inside. Now, what is this T and R? T and R means what? Transmit, receive, transmit, receive, transmit, receive, transmit, receive. What do I have here? I have here all the what? All the services that is being supported by what? By SONET. They get multiplexed. You transmit them here. Some of them will be what? Dropped in here. Some of them will be what? Added here. And then what? Going through this what? The outer ring. Do you see the outer ring? You could also support the traffic on what? On the inner ring. It's in the other direction. One of them is a clockwise. The another one is a what? Counterclockwise. Did you get my point or not? It has dual rings. Not like what? Not like the, if you remember in 450, the 802.5. Do you remember the 802.5? I don't think so. You totally forgot. It's a ring network. How many rings? Just one ring. Either clockwise or what? Counterclockwise. SONET uses 2 rings. Now you might say, why 2 rings? You will see that. But did you get the idea? The traffic is coming here. From where? Multiple customers. Multiple customers. They get multiplexed. And then they what? Send it to here. Some of them will be dropped in here. Some of them will be added. Here, 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 and so on and so forth. And when you reality, this is what? This is the local rings, local rings. This is what? A metropolitan ring. This is a what? A regional link. One ring is connected to another ring, to another ring. And by the way, you notice the rings are connected to the other rings in more than one point. Did you get my point or not? Yes? In more than one location. Why? Because if something goes wrong with this one here, and if you do have only one connection, that means what? This one got isolated from what? Isolated from these. Did you get my point or not? Yes or no? Yes or no? Okay. So, why is this so special, this SONET? Let's assume there is a failure in here. Let's assume there is a failure in here between this ADM and this ADM. What will happen? The outer ring, the inner ring will what? Wrap around the what? The outer ring. Automatically. The inner ring automatically wrap around the what? The outer ring. So now what do you have? Look at my finger. Did you get my point or not? Is it still a ring? It is still a ring? You lost me? Okay, one more time. Here. 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 It is still a ring. So the ring is intact. Even though there was a what? There was a failure in here. Even though there was a failure in here, the ring is still what? It's still intact. Now you might say, Professor, what if there is a failure in here? If there is a failure in here, this one is what? Isolated. Did you get my point or not? But what I'm trying to tell you is that if there is a failure, a single failure at any point, the network will still maintain what? Operation. Will still maintain connectivity until the break is what? It's fixed. Until the break is fixed. Did you get my point or not? If they use only what? If they use only a single ring, and if there is a failure, there is nothing to wrap around. Did you understand that? There is nothing to wrap around. So they opted for what? Dual rings. All of these are fibers, by the way. These are fibers, optical fibers. Clear? Clear? Okay, good. So this is the dominant technology. This is a dominant technology for the what? For the SONET. We will see that WDM, the DWDM, also use what? Also uses rings, but it also uses what? It uses a mesh. Are you following? SONET decided that the rings is the best solution for them to interconnect what? Local networks with what? Metropolitan networks, with regional networks, and with the global rings. A lot of rings. Looks like what? Wedding rings. That's a joke. Oh, clear? Okay, good. Now let's move now to the DWDM. But before we get to the DWDM, we need to understand a little bit about optical components. What are the optical components? What are they? What are the devices that deals with what? Optical signals. So let's look at, first of all, the characteristics on an optical network. The transmission is what? Optical fiber. The switching could be optical, could be what? Electronic. Currently, most of them are what? Electronic. But the trend is toward replacing everything by what? optical. Why is that? If the switching is electronic, what does it mean? It means when the signal, optical signal, comes over the fiber, which is a what? An optical signal, needs to be converted back to what? Electrical, gets switched electronically, are you following or not? And then converted back to what? Converted back to optical. They wanted to eliminate that conversion from optical to electrical, electrical to optical by using what is known as what? Optical switching. We will see that shortly. The switching technology, again, it could be circuit or it could be what? Packet switching. So as far as the switching is concerned, it's the same thing here. Now, most prevalent deployment is the optical, electrical, optical switches. And this is the one that I was just telling you about. Operating at OC levels up to OC 192, demultiplex inside the switch into what? Inside the switch. All of these are demultiplexed into the STS1 electrically, switched electronically at the STS1 level, and then multiplexed onto the what? And to OC level. Did you get my point or not? Did you answer what that means? The signal the signal is at what level? OC level. Let's say OC 192, which is 10 gigabits per second. Inside the switch, they will what? Demultiplex, because the switch is electrical. Clear? The switch is electrical. They will demultiplex it inside the switch into what? Into all the way to what? STS1 level. STS1 level is the what? Is the 51.84 megabits per second. They switch the STS1 levels, and then they what? Multiplex the STS1 levels again. Clear? Using what? Using electronically, and then they convert it to what? To OC level. Network provider, again, can support requests anywhere from the STS1 level to OC 192. Again, as I told you, work is being done to increase the 192 all the way to what? 768, which means what? 4 times at that much. And the bandwidth is assigned on a what? On a per demand basis. The more bandwidth you get, the more bandwidth you ask, the more of these you will be getting, as I will show you in just a second. Okay, why optical? Why the trend is going to go through the optical? Let's look at the huge bandwidth. How much is the bandwidth? Anywhere between 50 to 100 terabits per second. By the way, what does that tell you? Even that 40 gigabits per second I was telling you about, it has not what? It's not fulfilling the what? The optical. And that is what they do is the following. They are going to multiplex several wavelengths over a single what? Over a single fiber, or where every wavelength can support what? 40 gigabits per second. I'm not sure, did you get this point or not? Did you get this point or not? Every wavelength support what? 40 gigabits per second. And you are what? You are, let's assume that you multiplex 100 wavelengths. What will it be? What will the total be? If every one of them is every wavelength, let's assume every wavelength is supporting what? Is supporting 100 gigabits per second, for example, and you multiplex them, you multiplex 100 of them, 100 of these wavelengths, then you end up with what? You end up with whatever the number is, 10 terabits per second or something like that, to be supported over a single fiber. Clear? Tera means what? 10 to the what? 10 to the 12. This is the first time you hear the word tera. You must have seen it before. So, terabits per second is what? Is 10 to the 12. Low signal attenuation. What does that mean? I don't need to put what? Regenerators along the way every what? Every half kilometer or every kilometer because the signal is degraded. In fiber, because you are transmitting using optical signal, which is much higher in the spectrum, the interference from outside is minimal. So here at the are you familiar with dB? dB is what? Every kilometer you will lose roughly what? 0.2 dB, which means almost what? Almost nothing. Are you following me or not? Almost nothing. So low signal attenuation, 0.2 dB per kilometer, less number of regenerators over the long haul distances. Immunity to electromagnetic interference. Electromagnetic means what? Radio signals. Radio signals, wireless signals, and so on. Well, signals that use the wireless links and so have no effect on the fiber whatsoever. Why? The radio signals are transmitting using which range? RF range. Whereas the optical is what? Much higher in the frequency. Clear? Remember, by the way, the frequency. The lambda, which is the wavelength, is equal to what? C over what? F. This one. This is what? Speed of light. So the higher the frequencies, it means the wavelengths are what? Shorter and shorter and shorter. Clear? Okay. So immunity to electromagnetic interference, what does that mean? It means that you will generate a low bit error rates and the minimum end to what? Minimum end-to-end delay as well, because you are transmitting at an extremely high rate. Highly secure. Why is it highly secure? Why is the fiber highly secure? It's very hard to tap into the what? Into the fiber without breaking it. Did you get my point or not? It is very hard to tap into the fiber. When we talk about security, it means what? Somebody is tapping on your line. Are you following me or not? Somebody is tapping on your line and stealing the signal. The fiber is very hard to tap it. And if you tap it, there is a possibility that it will break. And it will break, it means what? The signal is gone. Did you get my point or not? So highly secure, low signal distortion, suitable for carrying digital information, low power requirement, does not require too much power, lighter weight. Why is it lighter weight? The fiber is so thin. Lighter weight, less space, it takes less space, non-flammable, safer and more cost effective, and so on. So clear? When I say more cost effective, I don't mean, in other words, if you compare it with the amount of data that it is what it is supporting. Did you understand what I just said or not? In other words, I'm not saying that it is what is cheaper than telephone line. It's not cheaper than telephone line. But if you support the same rate using telephone lines, you need what? A large number of what? Telephone lines, equivalent to how much what? One fiber can support. So if you add the cost of all of these, telephone lines will be more than the what? The cost of a single what? Of a single fiber. Clear? The beauty of the wavelength division multiplexing, like I will show you in just a second, is that the providers did not need to install what? In new fibers. The existing fibers, they can use the existing fibers, but multiplex what? More wavelength on a single fiber. Before it was what? One wavelength per what? Per fiber. Right now they are able to what? Multiplex several wavelengths on a single fiber. So instead of what? Extending, for example, 10 fibers, let's assume they need what? 10 wavelengths. And instead of extending 10 fibers, they will extend only what? One fiber, and they multiplex how many wavelengths? 10 wavelengths on that single fiber, which I'll show you in just a second. Clear so far? Okay, good. Now, the optical transmission system, what does it consist of? Let's see if we can go over it. This is, by the way, material of EE. You will study it if you take this course. EE 558, which is called optical something, optical communications something, optical communications, whatever. Okay, we don't need that much here. I just want you to understand the components. This is the information source generating what type of signals? Binary signals. Digital signals, binary signals. Then I have the what? The modulator. This is a what? An optical source. For example, a laser generating what? Light signals. The information is going to be modulated onto the light. Clear? I want you to think about it this way. If this one, for example, was on-off, the light would look like what? On-off, 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 on-off. Or multiple what? Multiple colors of the same what? Of the light signal. Multiple colors means what? Multiple levels. So it gets modulated. So the information source, again, generating a digital signal. We do have what? The optical source, either a what? A light emitting diode. We call it a light emitting diode, or what? Laser diode. Laser, of course, is much higher quality than the what? Than the light emitting diode. Clear? Oh, so the laser generating the light signal, it gets the information, gets modulated, then it's transmitted over fiber. Whenever you see in the textbook or in literature or whatever, when you see a link and then there is a what? There is a circle behind the link, it means what? That's an optical fiber. That's an optical fiber. So it goes optical fiber. It goes to a what? an optical amplifier or a generator and a regenerator. And again, as I told you, this one does not need to be spaced every half kilometer. Every 10 kilometer, you might need one. Did you get my point or not? Oh, so you get an optical amplifier. At the receiver, what do you have? An optical detector. An optical detector, photodiode or what? Phototransistors. Are you following me or not? Okay, where the what? Where the optical signal is going to be detected and converted back to what? To electrical signal. Thank you. Clear? Clear? Okay, good. Now, let's look at the fibers. We have what is known as a single mode and a multi-mode. Which one do you think is better? Single mode or a multi-mode? A single mode is much better. Clear? What does that mean? The fiber, by the way, consists of what? Consists of three parts. What is known as the core. This is the core. And there is the what? The cladding. And then there is the what? The jacket. Jacket. It gets cold in the winter. Clear? So the fiber consists of three parts. This is the three parts. This one is the what? Is the core. The core is most important because that's where the what? Where the optical signal is going to be traveling. The core and the cladding and then the what? Jacket. Jacket is to protect it from what? From outside. You know, you might say protect it from what? From rain or something. It's against erosion and so on and so forth. Clear? In a single mode, the optical signal will take only a single path from the transmitter all the way to the what? To the receiver. A single path. And you notice the diameter of the core is what? 10 micrometer compared to the whole thing. The whole thing is roughly what? 125 micrometer. Clear? Is that thick or thin? It's very thin. It's micrometers we are talking about. Clear? What happened here in a multi-mode? What do you see? The core is what? Is wider. The core is wider. It's now what? 62.5 micrometer. Clear? The optical signal might take what? Multiple paths from the source to the what? To the destination. When they take multiple paths, what does it mean? It means the delay will be variable. Do you agree? The delay will be variable. So when you combine the signal in here, the signal will become a little bit what? Smeared. A little bit smeared. A little bit distorted. Did you get my point or not? Which means what? It can support lower rate. This one can support lower rate than this one. So multiple rays follow different paths, result in pulse spreading. Intersymbol interference, reduced data rate, impact worsen with what? With the distance. The longer the fiber is, the effect will be what? Will be worse. Clear? Clear? Now, inside the cores of the actual networks, they are all what? Single mode fibers. But at the edges, they could use what? They could use multi-mode. Why? This one is cheaper. Are you following? This one is cheaper. And at the edges, the amount of traffic is not as much as in the what? In the core. Because the core is taking what? Aggregate traffic. Clear? Oh. Now, the question then become what? What wavelength should we use? So they did experimentation on different wavelengths, and they measured how much loss in the optical signal, how much loss per kilometer, in dB per kilometer. What did they end up with? They ended up finding that the best wavelength there is what? Is the one at what? 1550 nanometer. 1550 nanometer. They also saw that what? That in the 1300 nanometer, there is also what? A small dip in here. All of these are what? Are measurements. So they ended up with what? They ended up, they saying that if you want low attenuation, your wavelength should be around what? Around 1300 nanometer to what? 1550 nanometer. Clear? So they based what? They based, let me show you so that you understand. They based their grid, this is the standard grid, they based it on what? On the 1552.52 nanometer. This is, everything is based on this. It's centered around this. Sorry. This is another wavelength, a third wavelength, fourth wavelength, fifth, and so on. And you can see that the length is what is clustered around the what? The 15, because they saw that this is the best quality of what? Wavelengths for what? For optical fiber. Now, wavelength division multiplexing, we will start this next time, but let me just show to you the idea behind it. What is the idea? We have multiple wavelengths. I don't want you to think about these as what? As cable. This is just illustration purposes. Multiple wavelengths, lambda 1, lambda 2, lambda 3, they are going to be multiplexed on a single what? On a single fiber, and every wavelength is going to have what? Is going to have different what? Modulation. Different type of, so for example, this wavelength is carrying what data? Ethernet data. This one is carrying what? IP data. This one is carrying what? SONET data. Or SDH data. Did you get my point or not? In other words, these wavelengths, they don't need to be modulated from the same what? Protocols. From the same protocols. It could be what? Different what? Different types of what? Different types of data. Ethernet, IPs, and so on. So, okay. We'll continue with this next time. Clear? Okay. We'll continue this next time.
The time is 19 o'clock.